Okay, so today we're going to talk about higher derivatives. So what do I mean about higher derivatives? Well, this is the notion of taking a derivative of a derivative. So the idea is, let's say you have a function and you take the derivative of it, and that gives you f prime. Well, what if you took the derivative of that derivative? And if you did that, that would actually end up giving you f double prime. So we're going to do that here. So the first and probably most common derivative is higher derivative is the second derivative. So the second derivative basically says that if we have something called f prime of x and f prime of x is differentiable, then f double prime of x is just going to be the derivative of f prime of x. So that should be an f prime of x there. So just to do a quick example here, basically, this is going to be 5x cubed minus 4x squared minus 3x. If I want to find the second derivative, the way in which I would do this is that I'm going to say that this is, we'll first find f prime of x. So that's going to be 15x squared minus 8x minus 3. And then if I want to find f double prime of x, we would take the derivative again, and this is going to be 30x minus 8. So that will be our second derivative. Just as an additional note here, for notation, most often I will just use the f double prime of x notation for the second derivative, but in Leibniz notation, you will occasionally see something like d squared and then dx squared. Again, don't think of this as some kind of exponentiation, but there's basically 2's there. Or of course, if it's y, you can also do that as well, if y is equal to f of x. Okay. So, of course, the natural question says, well, if you have a second derivative, can you have third and fourth and sixth and so on derivatives? And the natural answer, of course, is yes. So if we start with something like f of x equals x to the fifth, and I say, let's find the first derivative, we apply the power rule, that gives us 5x to the fourth. This, of course, a normal derivative is sometimes known as just the first derivative in the context of higher derivatives. So that's the first derivative. And then the second derivative would be the derivative of that. So this is the second. So that's going to be 20x cubed. And then we can take the third derivative. Notice that sometimes this is called f triple prime of x. So f prime of x, f double prime of x, f triple prime. And this will be the third derivative. So we take the derivative again. That's going to be 60x squared. And again, we can keep going. Typically, what we do after we use 3 prime markings here is we typically just notate it with f and then some open parentheses, and whatever the derivative number is will go up there. That's just the fourth derivative. This is going to be, 120x. The fifth derivative will just be 120. And then the sixth and any subsequent derivatives in this particular example will be 0. So again, as a concept, we can take derivatives forever so long as the functions are differentiable each time around. So what is the meaning of the second derivative from a physical standpoint? Well, we know that f prime of x is the rate of change of f of x. So that would mean that f double prime of x, the second derivative, is going to be the rate of change of f prime of x. So if we go back to what we talked about in the last video, where if we have a function s of t, and that gives us the displacement of an object at time equals t, we know that v of t is the velocity at t, and that's because velocity is the rate of change of displacement. But if we were to find the second derivative, s double prime of t, the physical meaning, of course, would be the rate of change of velocity, which is more commonly the acceleration. So acceleration will be s double prime of t. Okay, so think about, being in a car and you hit the gas and you're accelerating, how quickly you increase your speed, how fast you go from 0 to 60. That's an indication of the car's acceleration. And you'll see that as you get to higher derivatives, there's a third derivative, which is sometimes called jerk, which that is something that very rarely gets talked about, but it's that notion of kind of feeling jerked around if you're accelerating too quickly or braking too quickly in a car. From that point, the fourth derivative, fifth derivative of displacement, those have less and less physical meaning as you go higher up. Again, you could calculate them, but there's not really much that needs to be said there. So even in a Calc 1 class and even in higher math classes, oftentimes the second derivative is usually about as high as you most often get. Occasionally you'll see third derivatives, but first and second derivatives are going to be the most commonly used in just about every application that you see. So let's just do an example so that we can understand how this would work. Again, we'll do a practical example. So let's say a ball is thrown upward with an initial velocity of 5 feet per second, and we're going to say that it has an initial height of 200 feet. Then if I were to calculate s of t, it would actually be given by this particular contraption here. So this would be the equation which represents that motion. And if I were to start calculating the velocity functions, you'll notice that the velocity is going to be the derivative of this, which is 5 minus 32t. And then if I were to calculate an acceleration, you'll notice that this is just the constant negative 32. And it turns out that, again, the units here, since this is in feet, velocity is in feet per second, and acceleration here is going to be in feet per second squared. The number 32 feet per second squared, again, it being negative, is actually a real number of acceleration. This is actually how quickly things fall in Earth's gravity, a constant 32 feet per second. So this actually does give the real value that you would get. Anyway, I hope that you found this video helpful, and as always, take care.